Dear
Sure.
participants, Dear participants, welcome to the seventh session of NEPM 2021, organized by Department of Mathematics, Sacred Heart College, Chalakudi. This program is envisioned to keep the spark of young mathematics aspirants. I would like to offer a warm welcome to our eminent resource person for the day, Dr. Neeraj Kumar Dhanwani, postdoc fellow, IISER Mohali, who will be delivering a lecture on geometry after Euclid. I invite Dr. Nitin TJ, Assistant Professor, Department of Mathematics, Sacred Heart College, Chalakudi, to introduce the speaker.
Okay. Okay, dear participants, our chief guest for this session is Dr. Neeraj Kumar Dhanwani. He has completed his undergraduation from Shia College, Lucknow University, and post-graduation from Devi Ahalya University, Indore. He obtained his PhD degree from IISER Bhopal, and his thesis title is Commutativity of Periodic Mapping Classes and Their Representations as Words in Dane Twitch. He has published papers in international journals. He is an active researcher and presently working as a postdoctoral researcher at IISER Mohali. In today's session, he will talk about geometry after Euclid. Over to you, sir.
Okay. So shall I start? Thanks for
Ah,
the
Yes.
such a
yes, sir.
uh, it's a, like thanks for this welcome, and I thanks to the all the organizers for giving me this opportunity. Uh, okay, when I planned this talk, I planned in some other way, but I don't know how it's going to today. So okay. So when I'm talking about the geometry after Euclid, uh, first I should understand what was the geometry before Euclid. So okay, let me put like this. We from the beginning of our understanding, whenever we try to understand something, we started to think about the things. We always curious about the geometries to shape of the things. With the our basic knowledge, we try to compare the things, try to see which is more smoother for us, which is not. We built up the wheels using the property of circles. We built up lot of things, the roofs of the huts based on the geometries. But still, that is not the geometry which we study today. That's very different from today's geometry. Before Euclid, or I say before 300, 600 BC, we were more interested about the computations, computing area, computing volume, looking the surface areas, how much material we want to build, that is volumes, and so on things. But that are computations. That's something a computation. The first known theorem in the our mathematics is, I think this is a first theorem which someone proved using not only using the computation but using the axioms which we are used today. Uh, this theorem is many literatures known as a basic property of a triangles theorem also. And this is a, if I'm not wrong, NCERT book introduced first times in the ninth class. This theorem says if you have a triangle, then if you draw a line which is parallel to your baseline, then it will cut your triangle in the sides to be the common ratio. More oftenly, we remember this theorem as if you draw a parallel line from the midpoint of the one side of triangle, which is parallel to the base, then it will hit to the midpoint of the other side. If you assume D is a midpoint, and if you assume D is a midpoint, and this is a parallel line to the AB, then E will be the midpoint of BC. That's one of the basic corollary of this theorem, and I'm sure all of us have seen the proof of this theorem somewhere in our basic studies. Even after this time also, we were not sure what is the definition we are using here. We were not very sure about what our meaning was in line, what is the meaning of the parallel. So these things first time very much formulated, or we say the correct word, maybe correct word is written down someone, is the Euclid in his book of the Euclidean of Geometries, which I don't know if it exists today or not, but there is very might think that exists. The original copy of that book is exist. So he was the first mathematician, philosopher who tried to formalize the things, who tried to give the definition, proper definition, what is the meaning of what is not any difference from the our and others meaning. He said what is the meaning of what is the meaning of point, what is the meaning of line, parallel line, and what's are the in abstract manner. We don't need a model to understand these things. So his point meaning is anything which don't have any volume or any area. His line was which don't have any volume, area, but have length. Parallel lines, his definition of the parallel lines was very different what we used to learn, that I will be maybe show in some time. And so on, the what are the angles and so. So Euclid was the one who built up our geometry in the way we used to learn today. And his geometry, as like a mathematics, is based on some postulates. What are I always think what the difference in mathematics from the other things, the other sciences. That I choose to found of the line. I think this is from the book Dialogues on Mathematics. That the biggest difference is math is built by the man. It's a thing which is created by the man. It's a language. That's why it's art. It's a science at the same time it's art. So what are the postulates Euclid created for his geometry? What his meaning of the geometry? So these are the 5 postulates which he assumed before to work start, which was very obvious. The geometry we know, for that this is very obvious. You assume any R2 plane and you think any 2 point, then there should be only one line. What the meaning of the line was? The meaning of the line was a path which is have a minimum distance between these 2 points. That he called a line or something today we know as a geodesics, or maybe some different definitions are there for them. So this is the first thing. There is a unique line if you have any 2 points. Other thing was infinite length. What was the meaning of that? Infinite length meaning was if I give you any part of the line in the plane, you can increase it at the both end till infinity. You will never hit again to the line if you are going to increase it both the ends. Construction of the circles. His other postulates was that you can draw a circle at any point with any radius. So as again, you take any point in the R2 plane and draw a circle of any radius, whatever you want. For The first timer who was looking this, these are basic definitions which we always assume in our geometry, but they are the first postulates. The fourth one is right angle are equal. Whenever you draw a right angle, that is should be equal to the 90 degree. That's a meaning of the right angle. Now the coming about the most debatable, most studied postulates is parallel postulate. What was his meaning of the parallel postulates was this: if you have a straight line crossing two parallel lines to another straight parallel lines, straight parallel lines, then the sum of the angles sorry, they're not parallel lines, is the consequences of that. Another two another lines, straight lines L and L prime, then if their angle of the side, their sum of angles is less than pi, then they will meet in then they will meet just I should stop. Then they will meet. What is the meaning of this? This is his parallel postulates. I should define what is my meaning of this and what doesn't. So if you have any two lines, say any two lines, you draw third line. If the sum of these two angles is less than 180 degree, then if you are going to increase this line to the infinity and this sum is less than 180 degree, then they will should going to touch at some point. This is his parallel postulates, and from here or from this or we say from there, his definition of the parallel line was two lines is said a parallel if they don't intersect in the plane. We say two lines are parallel if they don't intersect in the plane, whatever the plane is. So any question till this point? Okay, good. Please feel free to ask a question at any point because otherwise time is very much. Okay. So one thing I should not forget this. This topic is very basic and you can find it in many books in the introduction part. For example, in any hyperbolic geometry book, this is in the introduction part or somewhere. One or two references I like is Carlin series hyperbolic geometry book, ECH non-Euclidean geometry, and Anderson hyperbolic geometry, and there are more. So that time when this postulate Euclidean puts up, from that time to the very long time, people were very curious why these postulates are necessary. Look, first one is okay, people will always be okay that there is a unique line because they experience a unique line between any 2 points, which is a straight line, their meaning of the straight line. Infinite length, they will always this one. But the fifth postulate, the parallel postulate, people was not very sure that this is necessary to assume. they always thought it can be proven just based on the first four postulates. So if I assume for four postulates, I can deduce this thing using the some logical statements, which we today call the language of mathematics. And many mathematicians try to prove this or disprove this. But what they got is just the equivalent statements of this statement. What are they? Some of them is very useful to understand today's geometry. This one which himself Euclid gives. Sum of angles of triangle is 180 degrees. This was the first equivalent statement of this Euler postulate, that whenever you have a triangle, its angle sum should be 180 degrees. Second, the second statement was by the, sorry for this inconvenience, I'm just stopping the sharing for the 1 second. I hope the screen is visible now. So the thing is, the second statement which was given by is by Proclus. This was in between something like 410 AD to 485 AD. After that, so it took us 700 years. People to what should be the we could do with this, and his statement was one of the statements which we used to learn. If you have a line and a point outside a line, then you can draw a unique line from this point P which is parallel to L. The third equivalent statement by Wallace in 1663. His statement was also very interesting. After coming through the some more literature, he gave the statement there exist similar triangles of different size. Is this statement make sense? What is the meaning of the similar triangle? The similar triangles is a triangles whose all angles are equal. They have a property of AAA. If we say two triangles are equivalent, then it is only when their corresponding angles are the same. This angle is equal to this angle is equal to this, and this angle is equal to this. Then we say these two triangles are the equivalent. Now, it is easy, may not be easy, but this is an interesting exercise to see that these statements are actually equivalent, or there are more statements which are equivalent to this, which many mathematicians gave in the different time periods. But these are the three which we generally study in our graduate till the 12th class of high school mathematics. Okay, but still the question was, is it five postulates was necessary to construct a geometry? And people still not believed till 1600th century, even after the 13 more than 2000 years after the Euclid, people were not ready to believe that these are the all. So people come up with some more ideas. Okay, before going to be more geometric part, this is a one fun part, the tiling of the plane. What is the meaning of the tiling of the plane? I'm sure that we all have seen the tiling of our room surfaces. And at a time, sometimes we should be curious that why we are always the tiles are the square shape or a rectangle shape. Why not some other shape like a hexagon, pentagons? Why not others? So what is the meaning of the tiling of the plane is you have a plane R2, you want to cover this up, the cover complete plane by only one object. Say whatever object you take, I am taking a triangle for my convenience, and its copies. It's isometric copies. So can we do that for triangles? Okay. First I place my first triangle on this. Then I will just take the other piece of copy. If this is A, B, C, my first triangle, I will take another copy of the triangle and put up along this side, such that this B angle will be match up to the C angle. So I will draw a one more pen triangle here. This will be the A angle. Now again I will put the triangle here. The same copy, I am not changing the triangle. The same triangle I am placing again and again, and so on. This side I will again do the same thing. I will place the A here, B here, then so on. Go. Are you getting the idea of what I am trying to do? I am trying to translate my triangle from one point to another point. It's also called a tessellation of the surfaces. This was a interesting question, was why this is a only possible with the triangles and squares and other quadrilaterals, with particular type of quadrilateral. Why not by the any type of thing? That comes again by the very easy geometry, and might be I am leaving for the student that any hexagon, if you take the regular hexagon, that cannot cover your R2 plane. If my voice is clear, is any type of noise disturbance or something? Is it fine till now? Am I audible?
Yes, sir. Now you're
Sir,
audible.
sir, please repeat this
Is my
concept again.
that I will. So my voice is clear now. Okay, thanks. what I was saying this that if you have a one figure of geometry, one type of triangle, one piece, you take the mirror images of that. You take a same type of that again and again and try to cover your R2, which called a tiling of surface or tessellation of the surface, and many other names are there, filling and so on. So this is not possible to cover R2 by the hexagon. That's because of the sum of the angles. You just try to see that sum of the angles is not possible. If they are at this point, the sum should be 180-degree, which is not possible if these are the regular hexagons. So this was again a difficult one. What if we have some other type of geometry? Whether there is a possible or not. Now up cover to the models, how we understand the geometry. One way was you construct a geometry, try to understand that. But still, we need some formulas, we need some theorems, and for that we need an abstraction. There are a lot of models to understand the geometries are Poincare model, Klein model, and so other Euclidean model and so on. Two, I am going to, one is Poincare model and other is Klein model. That these models were more or less based on this one idea. This idea was to understand what will happen if you have any geometry you have, then instead understanding the geometry itself, you try to understand its associated thing, which basically we do in mathematics. If we are doing something, then instead of doing that thing directly, we try to understand its nearby thing and then apply to our theory. So they gave the idea to understand the isometric groups. What that meaning of the isometric groups are, you find out all the isometries of your plane. If you have R2, you translate your thing by any length. There is no difference in the plane. Any question? Okay. So this is a one of the idea. The other thing is, now the problem was to understand how many isometries are there. How many isometries comes by the name is they doesn't change the distance. At the same time, it's my understanding for time being is just it not distract the shape of your plane. These are some models to understand this. Maybe I will talk them, maybe not, but this is. So now, after that, it's so much studies. Still, we are the same question: is there are some other geometry? Okay, first we'll give to the easy answer. Yes, there are. We have familiar. Yes, we were familiar from the very beginning. Our Earth. Our Earth is not flat. It's a spherical. Sorry, my picture is not very spherical. It's some. What are the distance between those 2 points? Or what will be the shortest distance between these 2 points if we want to travel from here to here? So they will not be these lines. They will be something like this. or something curved, which we generally seen on our globe. Okay, it might not making a sense right now. Let me go to the very conceptual. So for this, what is our we are taking? We are taking S2 as our model. What other thing we need is points. So what are the points? They are the points, just every point on your sphere. Third is lines. So this is my definition. What I want to call the line, a part of great circles. So what is the meaning of the great circle? A circle which divides your sphere in equal two parts is called a great circle. So again, if you have a sphere, this is your great circle. One more can be this. One more something can be this. And so on, other things. And this is very interesting to see that this also forms a complete geometry with all the different understanding what we have about our Euclidean geometry. Geometry which gives by which follows all the laws of Euclid. Obviously, when I'm saying this is not a Euclid geometry, it has to differ. At what points it differ? So one thing is, by this definition of the great circle, there is no any parallel line. If you draw any line on your surface, the other line has to intersect it. Easy to see. What about the triangles? I shown there is a one triangle is possible to construct. What about their angles? Some. Again, not easy to see, but interesting, always bigger than it. This triangle sum is always bigger than 80. This is a one thing which is can be done, but still we are not happy with this because still it's not giving our answer of the postulates one. It's not satisfying the properties, yes, but it's not giving me some different for which we are looking for. Our search was ended by some work by the Gauss, Lambert, Lebowski, and some other mathematician in the during the time of I think 1800 or nearly 1700, and when they come up with some ideas of how you construct a hyperbolic geometry. So the hyperbolic geometry is completely opposite than the spherical geometry, and it's a different one. Okay. So instead of going to the firstly to the geometry, let me give the one example of this geometry. So what you need for the geometry, you need a space. Let me take half of R2. Half of R2 means I will take all those points x comma y such that y is positive. I will not consider the below one. This is your space model. Generally, we say it as 2 points. Points are just points. We're not changing anything there. Line. What are the lines there? So if you think any 2 points, how are you going to join them? That's about the question. And very intuitive idea was to join them via circles. Not a random circle, but those circles whose center lies on the x-axis. So lines are the part of semicircles whose center on x-axis, which is x comma 0, x very 0. But is it a problem solved? What if we do when you have a 2 point like this? You don't have any circle. Okay. What we will do, we will assume one more type of line. Those lines which are perpendicular to the x-axis. Euclidean lines which are perpendicular to x-axis. And if you have done high school mathematics, it is easy to see that these circles also forms a 90-degree angle with the x-axis. Why? This is a center, so this is a diameter, and any tangent which touches the circle on the diameter is a 90-degree. So this the point of the contact have a 90-degree. Okay, is these two together solving my problem? Is these two are saying me there may be contradiction in the parallel postulates? Yes. One thing, I am saying these things and I hope you are believing on me that all constructions are the possible. But it's very interesting to see by your hand, and it not required anything other than very basic complex analysis to construct all these things, that this is actually a possible. Okay, let me show why this is differ under parallel postulates but satisfied every other 4 postulates. Again, I had this x-axis. I am just taking the upper half. Sorry for this. This is again too easy to see. If 2 points are not in the straight line, straight vertical line, then there exists a unique circle whose center lies on the x-axis and passes through these 2 points A, B. Or to prove this, you don't need a lot of knowledge of, you just need to understand that this distance is equal to this distance, and this is a secant and this is a chord, which is, if you have a perpendicular, then it's divided by the 2 equidistant ones, and you construct like that. There's a unique circle like that. Why we need this? What about our first postulates in the Euclidean geometry? There is a unique line. We have. The first postulate is true. There is a unique line if you give me any 2 points. Second, these lines will never end. When I'm saying this never end, is I am making a sense? I don't know. Because I am ending here. My line is starting from this point and ending this point. But if these points are in our space, no. So this is like an edge which you are never going to achieve. This is like a place which you can see but never touch. So okay, so this is something which hard to believe, but believe me, whatever distance I will define on this, in that distance, it will never be touch this point. Third, so you can always increase the line. Circles, you take any point and draw a circle. Because you can always take a distance. Okay, by the way, I drew the circle the same way as I drew in the Euclidean geometry, but it's difficult, very hard to prove that they are actually same. But there are difference. There are difference between the centers. Hello, am I audible? So last thing, what was I saying? Am I audible? Is there?
Yes, sir.
Okay. So if I'm correct, last thing I was saying that about circles. Yeah. So okay. So circles. This is differed by the centers, and this is hard to prove. But okay, for this thing you believe on me. Right angles, by my definition, they are equal because I am defining them as same as in Euclidean geometry. If two lines intersect, how you find the angle between two circles? By looking their tangents. And for the lines, you already knows how to calculate this angle. And that angle I am defining as my angle. So this fourth postulate is also same. They are the right angles. Fifth one. What about the fifth one? Are we achieving something? For this, we need some equivalent statement. So shall I go back and check it out? What are the equivalent statements we have? But okay, first I try to make it again, the picture. This is my plane. If I have this line, and this is a point outside my line, which is the obvious line you think we can draw from the P, which doesn't touch L? A straight line. Sorry, that's my drawing. My drawing is very bad. Okay. So this is, but it's only one. What about others? Can we draw more? Remember, try to remember a few times before. What was the equivalent statement of the parallel postulates? If you have a given a line and a point outside a line, you can draw unique line. So if that is fails here, you need one more line. How you do that? You try to see that there is a possible to draw a circle which passes through this, or something goes like. I'm leaving on you to construct this thing. That is just need a high school geometry. How you are going to construct a circle. If you have a one circle, how you construct another circle whose axis lies on the same line, which is the diameter for the both ones, and they don't touch. That is it. So this is a way, at least I am showing you two lines. And if you are believing on me, there are infinitely many lines. For every this point, we can draw one. So great, we have some geometry which is different from the Euclidean geometry. Why this is important? First of all thing, this is very useful. In the low dimension topology, this is a geometry. This is actually a basic geometry which you need to understand the hyperbolic geometry. What
Sir,
more?
please repeat this configuration.
Sorry?
Sir, please repeat this representation.
Representation. I don't know. So I am saying why this geometry is important. This geometry is, this is a very big theorem by the Thurston and so on people, that in the dimension 2, the most obvious geometry in the mathematics is hyperbolic geometry. Even this statement is vague, and please go for more correct statement of this. Right. This is something. Now, from the at the end, let me try to compare these three geometries. What are the differences and what are the similarities they have? Models. For Euclidean model, you have R2. For spherical model, you have S2. For upper half model, you have upper half plane. When I'm writing 2 above, that means this 2 is something have meaning. This 2 is a dimension, because I'm just talking about the length and height. There may be other directions also, which we 3-dimensional geometry, 4-dimensional geometry, and so on. There are classification for these geometries, but in 2-dimensional, these are the 3 geometries. Definition of the points, angles, this we keep the same in all 3 geometries. At least for these 3 models. What are the lines? Lines are Euclidean lines. Here, great circles. Here, we have 2 different types. One is half circles and vertical lines, which are perpendicular to the x-axis, perpendicular to x-axis. Parallel lines. How many parallel lines you can draw? In Euclidean geometry, unique. Unique when you have given a line and point. So this is a line with a point, is spherical when there is no parallel line. So you have no parallel lines, but in hyperbolic geometry, you have infinitely many. Angle sum, sorry, this little triangle. If you have a triangle, what is the angle sum?
180.
In Euclidean geometry, yeah, someone was saying something. Okay, it is actually pi. In spherical geometry, more than pi. In a hyperbolic geometry, it is always less than pi. This is a very nice classification. Euclidean geometry, as one of the equivalent statements says, it have similar triangles of different sizes. This, I think everyone knows that you can draw two triangles whose all angles are 60°, but length of sides are different. So you have different sides, different area. But in these two geometries, if you have a similar triangle, they are congruent. So if angles are equal, their sides also equal. This is also a point where these two geometries is very different than the Euclidean geometry. Try to recall that in high school or inter, somewhere when you are reading the similar triangles and the congruence triangles, you have a property of AAA, but this property was not here. These two angles are similar, but they are not congruent. But in the geometry which we are today discussing, hyperbolic, this is always true, that if they are similar, they are congruent. I will stop here. If there are questions, I'm happy to take.
Thank you, Dr. Neeraj, for such an excellent talk on geometry after Euclid. On behalf of the
Thank you,
entire
ma'am.
team of NEPM, I extend our sincere gratitude to you for accepting our call for giving a lecture and to interact with the students. Do anyone have any
I,
queries?
I,
Any further
uh,
queries? Today's link for feedback and quizzes, you can find that in the chat box.
oh, by the way, this picture is by the MC Escher, which is one of the brilliant artists in his time. He drew this picture. If you try to see this one, shall I make it zoomer if possible? This picture I took from the Google, and I have no shame because I am not able to do this at all in any cost. So this picture is actually had a name. It's called a fairy demon, I think, if I am correct. And this picture is also trying to show you that as you are going near to the boundary of the circle, your length is going to decrease. That is the meaning that you are never going to touch the boundary. This is also the some model of the hyperbolic geometry, but I'm always wondering when he was drawing this picture whether he knew about this hyperbolic geometry. doubt it. But this is also one of the great works that always inspires. Yeah. Sorry to interrupt you.
No, it's perfectly okay. Thank you, sir. Thank you. We're honored. Thank you, sir.
So there is no any question. If anybody is shy to ask a question, can we stop the recording? So if someone wants to ask something.
Lynette, please stop
Yes,
the
ma'am.
recording.
Fine, fine. Hope everyone is fine, like they are not asking queries. So thank you. Thank you all. Thank you, sir.
Thank you very much for the organizers once again. Hope I make little bit sense in the talk, and I just if you guys have suffered in the talk, very sorry from my side, and thanks for your patience. Thank you.
Thank you so much, sir. Thank you.